So I now request the session to be restarted by Samprada Pradhan. Okay, so yeah, very good morning to you. The session is on the site-specific investigation of shallow rainfall-induced landslides by Samprada Pradhan. So before I hand over the session to the expert, I would request Aditi again to introduce the speaker to the audience.
Now, I would like to introduce and welcome our next speaker for today, Dr. Samprada Pradhan. Dr. Samprada is a postdoctoral researcher at Durham University. She obtained her PhD from Durham University, studying the effects of rainfall and road construction on landsliding. Before her PhD, she completed her master's in geotechnical engineering from Asian Institute of Technology in Thailand. Currently, she is involved in the iModel landslide project funded by NERC grant UK related to understanding the effects of climate change on landslides in Malaysia. She is also working on the CRAFT project funded by AHRC UK, studying the risk of climate change-induced hazards on cultural heritage in Istanbul. Her research also includes the study of rainfall-induced landslides in Rize, Turkey, under the Newton Fund project supported by the Royal Academy of Engineering UK. Her research interests are slope stability, engineering behavior of unsaturated soils, numerical modeling, and experimental geotechniques. I welcome you and thank you, Doctor, for your valuable time.
Thank you so much. Can you hear me clearly?
Yes, you are.
Okay. Yeah, so hello everyone. Good morning and good afternoon to you all. I'm Samprada, and today I'm going to present a little bit about how we conducted site-specific investigation to understand the mechanism of shallow rainfall-induced landslides. And so this is the outline of my presentation today. First, I'll talk about rainfall-induced landslides and why is it important for us to be concerned about it. Then introduce rainfall-induced landslides, and then talk a bit about the methods that we use to analyze rainfall-induced landslides, and then move on to the coupled hydromechanical analysis using Plaxis. To demonstrate an example, I'll present a case study from my research in Nepal, and then give a brief introduction about the landslide scenario in Nepal, and talk about how we conducted site-specific field investigation and did testings, and how we obtained parameters for the modeling, and also touch a bit about the field monitoring program that we conducted in this research, and then present the results of the modeling, and I'll conclude my presentation there. So before I start, why is it important for us to study or be concerned about rainfall-induced landslides? So if we look at the top right-hand corner of the slide, we can see that globally there were over 380 landslides in the last 2 decades that caused 18,000 fatalities globally. And the actual number of landslides, fatal landslides and landslide fatalities could be much higher than what has been reported in this database, because because of various reasons. This could be because of underreporting of these landslides, or because there's a certain set of criteria that the disasters need to meet in order to be included in the criteria. So it's fair to say that there are much more number of landslides and fatalities across the world. And in the study by Petley 2012, he had also mentioned that the actual fatal landslides could be 20 times higher. Landslides could be 20 times higher, and the fatalities could be 4.3 times higher than what has been reported in this global database MDAT. So the whole point of why I'm mentioning is this: it's a global problem that's prevalent mostly in the hilly and mountainous areas across the world. And if you see on the chart at the bottom right, we can see that the Asian continent is much more affected by landslides as compared to other continents. We can sort of say that Asia is a hotspot for landslide fatalities. So talking about rainfall-induced landslides, I think we all are aware about how landslides and rainfall is associated. So generally speaking, the several studies have tried to establish empirical thresholds for landsliding using the inventory of landslides and associated rainfall events. These are generally expressed in the form, in the power law form that I've written here, where where I and D are intensity and duration of rainfall, and alpha and beta are the fitting parameters. But the big question here is, can we actually use rainfall to accurately predict the landslides? This question has always been there, because we know that there are other factors that also determine whether a slope fails or remains stable, and this includes the local geological, topographical, and other changes in the slope that humans make. And when we are using these empirical thresholds to predict the occurrence of landslides, we are implicitly assuming that landslides can occur in any given slope with any initial condition or any geology or topography when a certain amount of rainfall occurs, or when a certain intensity of rainfall occurs for a given duration. So it's kind of a generalization that we make when we are predicting landslides. So these local geological factors or site conditions, they are relatively constant, how they affect the occurrence of landslides. There are other time-dependent processes as well that are related to the atmospheric conditions that determine whether a slope fails or remains stable. So as you can see on the figure on the right, these atmospheric processes like evaporation, infiltration, etc., they determine whether the slope can remain stable. For example, when the unsaturated zone above the groundwater table, which is continuously interacting with the atmosphere, so when there's a continuously dry period, evaporation and transpiration can increase the soil suction, which allows even steeply excavated slopes to remain stable for an extended period of time. The same slope at any given time, because of infiltration, may fail due to decrease in suction, which reduces the stability of the slopes. So what I'm trying to convey is that any slope, whether it remains stable or fails, is continuously changing with time as due to interaction with the atmosphere. So in order to understand how the rainfall-induced landslides occur, or more specifically how shallow landslides occur in that unsaturated zone above the groundwater table, it's very crucial to understand and simulate the transient and dynamic interaction that is occurring between the soil and atmosphere. And this is where we come to the numerical modeling of landslides. So it's a way how we can model the transient processes that is occurring in the atmosphere, which affects how the soil slope responds to it. So broadly speaking, the numerical modeling methods for rainfall-induced landsliding can be divided into coupled or uncoupled analysis. As Arash also mentioned briefly about this in his previous presentation. So within an unsaturated soil, the seepage process or the flow and the mechanical processes that related to soil deformation are highly interdependent. For example, when there is rainfall, infiltration in the soil changes the pore water pressure conditions in the slope, which in turn changes the effective stresses and causes deformation in the soil, or changes in the volume, which we generally call flow-induced deformation. And this same deformation of soil, the changes in volume in the soil, modifies the seepage pattern in the slope, or changes the pore water pressure distribution within the slope, which we generally call deformation-induced slope. So these hydraulic and mechanical changes are occurring simultaneously within the unsaturated zone as it interacts with the atmosphere. But in the first method, the uncoupled analysis, the flow and deformation analysis are conducted separately. So it's kind of a one-way road where the changes in the stability of slope or deformation in the slope due to pore water pressure changes can be considered. But on the other hand, the changes occurring in the pore water pressures due to deformation in the soil cannot be considered. This is one of the inherent limitations of such analysis. So, even if it does not capture this interdependence, but it's considered to be a relatively stable, simple method. And there are softwares available that we can use for such uncoupled analysis, and it is a really popular method as well. We can use softwares like CWN, Slope W, and Chasm to conduct such uncoupled analysis. On the other hand, the couple analysis, the couple hydromechanical analysis, the one that Arash was also talking about previously. So in such analysis, it captures the flow-induced deformation as well as the deformation in the soil due to the changes in seepage or changes in the pore water pressures. So when we are analyzing rainfall-induced landslides, it's very important to simultaneously predict the hydraulic as well as mechanical behavior of the slope in order to understand how the stability of the slope is changing with respect to the atmospheric conditions outside. And generally, the softwares like Plaxis and Sigma W are used to conduct coupled hydromechanical analysis. So talking briefly about how the unsaturated soil behavior that is modeled in Plaxis. As Professor Toll also mentioned during his presentation, that one of the models to predict the mechanical behavior of unsaturated soil is by using Bishop's effective stress concept, and Plaxis uses this concept to model the unsaturated behavior of soil. So the Bishop's effective stress parameter chi is considered to be equal to the effective degree of saturation in Plaxis, and the pore air pressure is considered to be negligible. And generally, the most common common model to model the hydraulic behavior of unsaturated soil is the well-known Van Genuten hydraulic model. So here I've expressed the equation in terms of degree of saturation. And everything about this is mentioned in the Plaxis manual, so I'll not go too much into this, but this is how the unsaturated soil is modeled in Plaxis. And to demonstrate an example of how we can use coupled hydromechanical analysis in Plaxis to understand the mechanism of rainfall-induced landslides, I'll quickly present a case study from Nepal from the research that I did during my PhD. So before that, I'll talk a little bit about the landslide scenario in Nepal. As most of us are already aware about this, but Nepal is located in the central part of Himalayan arc, which is considered to be one of the hotspots for landslides. So landslides in Nepal, there are several factors that are responsible for landsliding in Nepal, which includes earthquakes. So it's located in the central part of the actively moving Himalayan arc. So yeah, the co-seismic landslides are one of the most frequent ones. But at the same time, rainfall and other human interventions are also the other factors that have continuously led to several landslides and fatalities. There's increasing evidence that because of improper road construction or non-engineered methods of road construction in Nepal, the frequency of landslides and the number of fatalities are increasing, and in the last 2 decades, and we have seen a significant rise in the number of landslides. So it's a very concerning thing at present. And according to this global fatal non-seismic landslide database by Froud and Petley, between 2004 and 2016, almost 10% of all landslides in the world were recorded in Nepal. Although it sounds a relatively small fraction, it's quite significant, because when we think about the neighboring countries, China and India, they are like more than 20 times larger than Nepal in terms of area, but they only contributed to like 15 to 16% of the fatal landslides in this database. So what I'm trying to say is that Nepal being a relatively small country, there's a large number of landslides occur every year. So it's quite a big issue for my native country, Nepal. And in the last decade, according to this database, the national database called BIPAD by NDRRMA Nepal, landslides in the last 10 years caused loss of about 1,200 lives, and economic damage of more than 14 million in Nepal. It's the minimum economic damage and could be much more than this. And so, coming to the case study. So this for our case study, we selected a landslide at a road cut slope in Sindhupalchok district of Nepal. So Sindhupalchok district is one of the districts located in central Nepal, which is about 100 kilometers northeast from the capital city, Kathmandu. So it's a relatively remote area, remote part of Nepal. And according to the Varnish landslide classification, this was a shallow translational slide with a sliding depth of approximately 1.5 meter sliding depth. So while we were selecting this landslides, we selected this specifically because about 7 months before this landslide occurred in July 2018, the slope at this location was excavated, as you can see in the figure on the top right corner. So this slope was excavated very steeply to about 70 degrees to widen this road. This is a local road, about 12 kilometers of local road. So to widen this slope was excavated very steeply, and in the subsequent monsoon, the slope failed, extending much more higher than the road cut there. As you can see, the failed slope at the bottom right hand corner. So we selected this site because we wanted to know what caused the landslides. To be precise, like we wanted to know if it was just the rainfall that caused the landslide, the monsoonal rainfall, or there was any role to play. I mean, the road, we wanted to know if the road cut there had any role to play in the occurrence of this landslide. So we wanted to see how the rainfall and road cut interact with each other to trigger landslides. So basically, we wanted to back analyze the failure mechanism of this landslides to understand the factors that triggered it. So before going into the more numerical modeling part, so I'd like to say that there are three main things that we need in order to start doing numerical modeling. So these are we need information on the subsoil condition, and we need the soil properties, and we need the geometry of the slope. About the first two, subsoil condition and soil properties, when we are working in countries like Singapore or the UK or other developed parts of the world, I would say that it's relatively easy to obtain secondary geotechnical data that we can incorporate in our models. And but in developing parts of the world, especially in the remote parts of the developing countries, the geotechnical data is quite scarce. So in order to do any kind of modeling, we need to generate our own primary data and conduct a comprehensive set of testing in the lab in order to understand the subsoil condition, as well as to estimate the properties of the soil. And in that sense, we did a few in situ tests at this investigated slope to understand what the subsoil condition looked like. And we also we did a series of field investigations as well. And during those investigations, we gathered soil samples, both disturbed and undisturbed samples, and we brought it back to the lab at Durham and did testing. And we also needed information on the slope geometry in order to create the two-dimensional model. And for this, we used field measurements. So to start with how we gain the information on the subsoil condition, we drilled 2 boreholes at the slope. As you can see in the figure, the first figure, we drilled 1 borehole near the crown of the landslide and 1 near the toe of the landslide, so that we can obtain a 2-dimensional cross-section of the subsoil. So for this, we utilized the rotary drilling method. And in each borehole, we did a number of standard penetration testing up to a maximum depth of 7 meters. The figure in the top right shows the SPT profile at BH1 near the crown of the landslide. As you can see in this plot, that the subsoil condition was fairly uniform with an average SPT of about 14. So while we were drilling the borehole, we also encountered a few boulder and cobble sized materials, so which can be considered typical for the colluvial slopes like this. So Yeah, so we could only drill up to 7 meters, but that was good enough for us. In addition to the borehole, we also excavated a trial pit near the crown of the landslide. We went to a maximum depth of 1.5 meter for the excavation, and we did it manually as well. So at different depths within the trial pit, we obtained the undisturbed and disturbed soil samples. So on the second figure here, you can see that we extracted some core samples using open-ended steel tubes. And in order to prevent any loss of moisture, we sealed the core samples with paraffin wax, and then used more cling films to not allow the water from leaving the soil. So this is how we brought the samples to Durham in order to measure the in situ properties of the soil. And so from the samples, from the borehole samples and from the samples that we got from the lab, we did a series of testings in the lab. So as you can see on the figure on the right, it shows the exposed trial pit wall. So from the undisturbed core samples that we obtained from the trial pit, we determined the physical properties of the soil. So first we measured the water content, we measured the dry density, void ratio, and all sorts of properties like that. And based on that, we found that the soil near the ground surface at about 0.25 meter depth, it was quite porous than the samples that we obtained from greater depths, which is I think expected, because we have a lot of superficial cracks near the surface, and we also have some grass roots. So this creates a more porous structure, or like a structure with higher void ratio. And interestingly, we also found that the degree of saturation increased with decreasing depth. So the soil below 0.5 meter, you can see that it looks slightly dark. That's because the soil was relatively wet at this depth. And in the samples that we obtained from those depths, we found a higher degree of saturation than the samples above. And yeah, of course, yeah, obviously, we also did some particle size testing in the lab. So for that, we used the commercial laser particle size analyzer. And these are the distribution curves for the samples that I got from the borehole as well as from the trial pit. And most of the samples, yeah, they had very low clay content, about 12% or less. And the silt and sand size particles basically dominated the distribution of the soil. And yeah, so most of the samples that we obtained from the field, they were classified as either silt or sandy silt. And yeah, so on the top, it shows the samples that we obtained from the borehole, and at the bottom, it's the particle size distribution for the samples from the trial pit. And at the same depth, the particle size distributions were almost same for both borehole and trial pit. And with regards to the mechanical properties, I did a series of saturated triaxial tests in consolidated on drain condition. The figure on the top right shows the stress paths in PQ plot. So based on this, we estimated the critical angle of shearing resistance to be 36 degree based on the slope of this line, the critical state line. And to obtain the saturated permeability of the soil, I also did the constant head permeability test in the standard triaxial setup. So basically what we do in this test is we maintain a constant pressure difference at the top and bottom of the sample, so that we can allow water to flow from the top to the bottom of the sample. And we do it at different confining pressures and measure the permeability at these different pressures. As we allow water to flow through the sample, we measure the rate of water flow, and that's how we estimate the saturated permeability of the soil. And for the soil water retention curve, as David and Arash also mentioned previously in their presentation, that we use the high high suction tensiometers developed by Durham University to measure the suction. So the second figure here shows a small sketch of showing the components of the tensiometer. And on the top right, you can see that we created this setup to measure the soil water retention curve. And I used the discrete wetting and drying method to measure the soil water retention curve. So what it entails is that to obtain the primary drying curve, or primary wetting curve, we dry and wet the samples in different stages and allow the suction to equalize for a certain period of time. Like I did it for like almost 24 hours at a time. And then after equalization, we measure the suction using the high suction tensiometer there. And then after measuring the suction, we take the volumetric measurements using a vernier caliper. So that's how we obtain the volumetric water content and suction using discrete drying and wetting method. And if we look a little bit into this setup, so yeah, I think you can understand. But yeah, so I put a light brass disc on top of the sample. That brass disc had a small hole on it, and that's where I put the tensiometer to bring it in contact with the sample in order to measure suction. And so these are the soil water retention curves that I obtained from this method. So as you can see, sorry. So as you can see, the hysteretic behavior that we see between the drying and wetting of the soil. So if to obtain the drying curve, first I dried the samples in a humidity controlled environment and allowed some water to evaporate and measure the weight of the soil and allowed it to equalize for a period of time. And I did it in stages until it reached to a maximum suction of about 500-600 kPa. And then after reaching that point, I started to slowly wet the sample in stages in order to obtain the wetting scanning curve. As you can see with the lines with the cross lines between the drying and wetting curve. So that's how I obtained the wetting scanning curve. And for wetting the sample, first I dried the sample completely up to less than 2% gravimetric water content, and then started to wet it in stages. And then obtain the wetting curve there. And so from the set of tests that we did in the lab, we were able to obtain the parameters that we needed for the modeling. So this table shows a quick summary of the parameters that we used for the modeling. So I'd also like to point out that, like Arash mentioned, that it's very important to incorporate hysteresis when we are talking about coupled hydromechanical analysis. But one of the limitations related to this softwares like Plaxis is that we cannot incorporate the hysteretic behavior of the soil, because it's a bit complicated like to use this in the softwares like that. So in our study we use the wetting branch, the wetting curve, in order to model the hydraulic behavior of the unsaturated soil. And because it does make sense that when the water is infiltrating in the soil, then it's more closer to following the wetting curve than it is to following the drying curve. Although it's still debated whether what is the best way to do so, and there are different arguments to do that. But we found that it makes more sense to use the wetting curve rather than the drying curve when the hysteresis of the soil cannot be incorporated in the model. And and I would also like to mention that, like Professor David mentioned in his presentation, that the permeability of soil can be quite different in the field as compared to the lab. So for the top 0 to 0.5 meter, we used 2 times higher permeability of soil than what was measured in the lab in order to incorporate the effects of superficial cracks and like, for example, vegetation that influence the infiltration capacity of the soil. And by increasing the permeability by 2 times, we found that the results were results were more accurate, I'd say. And on the right hand side here, this is the simplified slope geometry that we created on the measurements that we made in the lab. And the 4 layers of soil that I have separated here, it's based on the hydraulic permeability of the soil. And so after all the comprehensive testing and in the field and in the lab, there will always be uncertainties in the model and uncertainties in the soil parameters, because it's a few boreholes that we drill in the field and a few tests on few samples that we do in the lab. So how do we know that what the model is predicting is actually correct? So this question always remains when we are dealing with numerical modeling. So what we did in our study in order to make sure, or how to, in order to convince ourselves and to others that the predictions of the model are accurate, we set up a field monitoring program at the study site. So the first figure on the left, it shows the field monitoring program that we conducted during our study. So it's a relatively simple setup that consisted of a rain gauge and 10 HS soil moisture sensors. So the 10 HS soil moisture sensors basically measure the volumetric water content of the soil. So we installed 3 sensors at 3 depths, 0.3, 0.8, and 1.2 meter, in order to capture the infiltration as well as drying that occurs in the soil. And we also equipped the monitoring station with a data logger that is specifically designed for outdoor uses. So the use of data logger was to, sorry. So the so the use of data logger was to basically record what the rain gauge was measuring and what the 10 HS soil moisture sensors were measuring. And with this data logger, we didn't have to actually physically go to the site in order to retrieve the data. So we could use the web-based platform to see the data, the change in data, as well as download it in real time. So it's a very useful equipment. So we continue this. Yeah, the figure on the bottom shows how the data logger looks from the outside and inside. Yeah, if someone is considering using using a data logger in the field, then I would highly recommend this. It was very useful for us. And so we continued this monitoring for about a year. So starting from 27th of March in 2019 to 28th of March 2020. And the figure on the right hand corner, you can see it's the results of the field monitoring that we did. So I'll not go too much into this, but we can see that we can easily see that the sensor located nearest to the ground at 0.3 meter responded most quickly, and responded to almost every rainfall event that occurred during the monitoring period. And the sensor that's at the bottom at 1.2 meter showed almost constant volumetric water content of the soil throughout the year, except during the monsoon season between June and September, where we expect most of the rainfall to occur. So we use the measurements in the field. So we use the measured rainfall and we use the measured volumetric water content in order to predict the model predictions. So that's what we call the model calibration. So before we made any predictions using this model, we wanted to make sure that the model predictions are accurate, or they are able to replicate what's going on in the field. And so we run a series of coupled hydromechanical analysis in Plaxis to calibrate the model. So as you can see in this figure, so we had measurements of rainfall from the field. So we use the hourly rainfall as influx on the outer surface boundaries of the model. And we compared the field measurements of volumetric water content with the predictions from Plaxis. And that's how we tried to calibrate the model. And the results here, the results of the model calibrations are shown here. So the first figure on the top left, we can see the changes in the volumetric water content in the field as compared to the volumetric water content changes predicted by Plaxis. So we can see that the model was able to capture the timing of changes in volumetric water content, or it was also for the overall pattern of change in the volumetric water content that occurred in the field was captured relatively well by the software itself. So at 1.8 meter and 1.2 meter, the fit of the model versus field was quite good. But at 0.3 and 0.8 meter, it was the model was slightly over predicting the volumetric water contents. Well, despite that, we were happy that the hydrological changes that were going on in the slope over different phases of drying and wetting was actually replicated by the model. And so that's how we did the calibration. And once we are happy with it, we use the calibrated model to back analyze how the case study that I showed previously, the landslide, occurred in the first place. So to back analyze the failure mechanism, we first did a series of coupled hydromechanical analysis, and at different time steps, we also added safety analysis in order to determine the factor of safety of the slope. So to run this analysis, we first obtained the hourly rainfall data that was measured in July 2018 when this landslide occurred. So we obtained this data from the nearby rainfall station. And we applied this rainfall as influx, as I showed in the previous slides. On the model, we tried to see when this landslide occurred and how this landslide occurred. And if you see in this chart in the middle, we can see that the factor of safety changes with every incidence of rainfall. I mean, and the dependency of factor of safety on rainfall is quite evident. And based on our analysis, we found that the factor of safety dropped below 1 on 12th of July. And during a long duration rainfall, low intensity rainfall event number 6. And this time frame was in agreement with what we knew. So we don't actually know the exact time when this landslide occurred, but the landowner of the site, he said that this landslide occurred before the 16th of July. So our result quite agrees with what was told to us. And yeah, so in order to understand how this landslide occurred, I have plotted the suction distribution at the time of failure when the factor of safety dropped below 1. So the figure in the first figure shows how the suction distribution looked like when the failure occurred. So we can see that as rainfall occurred and as the wetting front advanced into the soil, the soil suction decreased gradually. So at the two sections, section AA and section BB, I have plotted how the changes in suction occurred. The red lines in section A and BB show how the suction profile looked like when the failure occurred. And so at the time of failure, the wetting front had reached about 1.3 meter depth near the road cut at section AA and about 1.1 meter depth at section BB. So corresponding to that, so we saw that there were larger displacements at 1.3 meter. So the depth of the wetting front and corresponds well to the depths where we saw more displacements. So if we see at 3.6 meter, the displacements were relatively small. And we also see how the displacement in the slope increased with the occurrence of several rainfall events in the middle. And if you look at the figure on the first figure on the right, on the left hand, we can see that the model predicted larger displacements near the steep road cut in the model, and the displacement decreased with increasing distance from the road cut. So, and with infiltration at the time of failure, when the factor of safety dropped below 1, very large displacements, almost like 200 millimeters or more, were predicted near the road cut. While there were because of infiltration and because of because of decrease in soil suction. So we came to this understanding that maybe perhaps the road cut had some role to play, in the occurrence of this landslide. So we created a hypothetical model here without the road cut. So the geometry that I've shown on the top is it's a hypothetical model that we created in order to see if the road cut had any role to play. So for the two models, we kept the coarseness of the mesh same, the rainfall conditions were same, the boundary conditions were same, and only the road cut was removed from the model so that the results can be comparable. On the right, we can see that the how factor of safety changes with the same rainfall is quite different in the two models where there is road and where there is no road. So the first thing that we need to note that is by comparing the red and black lines is that when there is a road cut in the slope, it decreases the initial factor of safety in the slope. So when the initial factor of safety is lower, ultimately the slope becomes more prone to failure when it is subjected to rainfall, especially continuous rainfall events during the monsoon. The second thing is that the two models were subjected to the same amount of rainfall under same boundary conditions, and the slope without the road cut was safe throughout this analysis, with a factor of safety about 35% higher. So that led us to understanding that when we have a steeply cut roadside slopes like this, it lowers the minimum amount of rainfall that would be required for a landslide to occur in a hill slope. So what I'm trying to say is that it lowers the rainfall threshold for landslides to occur in the hill slopes when we have a steeply excavated road cut slopes like that. So this brings us to this understanding that we perhaps need suitable protection measures in order to prevent roadside slope failures to occur. So the final few things that I would like to repeat is that the coupled hydromechanical analysis that I have been talking about, it can capture the transient changes that is occurring in the unsaturated zone when it is subjected to the atmospheric drying and wetting conditions. And by using such analysis, by even without hysteresis, or when we even by incorporating the wetting curve, we can use this to predict and understand how the landslides occur, why the landslides occur, and when the landslides occur. And in order to improve the accuracy of the models, and in order to ensure that the model predictions are accurate or close to the reality, we need to, or it's better if we conduct site-specific field investigations, and field monitoring techniques also quite help. And finally, that when we have improper construction of roads, when we excavate the slopes too steeply in order to widen the roads or in order to build the roads, it can actually promote the occurrence of landslides during rainfall. So in order to prevent that, we need to make suitable interventions in order to mitigate these landslides or perhaps prevent these landslides in the future. And that's all for now. Thank you so much for listening. If you have any questions.
Thank you very much, Samprada. So I think it was a wonderful session which gave us a very good idea on the investigation schemes which are required at the field and how to bring out that investigations into a numerical model and try to understand what are the schemes or what are the points at which we can understand to say forensics related to the failure which has happened in the field. So it was really a wonderful talk. So now I'll open the session for some questions. Yes, we have some audience physically present here. They are interested for question. Yes, Sonu.
Thank you very much, Dr. Samprada Pradhan ma'am, for such a nice lecture. I would like to ask that because these boundary conditions, this rainfall, which actually try to simulate the rainfall event. So there is one is the horizontal surface and there is a sloping surface of this site, which you have modeled. So has it been incorporated into the analysis, the effect of slope? Because rainfall, application of rainfall boundary on slope is different event than the application on the horizontal surfaces.
Yeah, that's true. So it's true that yeah, it's a thing that we thank you for asking. So thank you for I need to repeat that. So when we so in Plaxis when we apply rainfall, so we don't have to worry about how the rainfall is applied. So we basically input the give the data to the software, and it automatically determines how the slope is rainfall is applied. For example, at the horizontal surface the rainfall is applied vertically, but at the sloping surface it is applied at a certain angle, so which is equal to the slope angle, so theta. So that's how the software determines how the rainfall is applied at the sloping condition. So it does it automatically.
Thank you. Any other question?
I have a question.
Yes.
I would like to ask you that for testing, like for finding out the mechanical properties, you have taken like CU test for C and phi. Any reason for that?
Sorry, could you please repeat the question?
So the question is, why should we be using a CU test for finding out the parameters of a failed soil slope?
We need the effective stress parameters in order to properly simulate the mechanical behavior of the soil. So we either have to do CU or CD test. So in comparison to the CD tests, the CU tests are relatively quicker. So and while we are monitoring the volume changes in the sample and excess pore water pressure changes in the sample, it's basically the same. We are basically getting the same effective stress parameters. So that's why I did the consolidated on rain test.
Okay, that explains well. So I have two questions from the audience or from the online or from the poll. Probably you can also look into the questions, but I'll just read out the questions for you. So it is the question that what value of volumetric moisture content or volumetric water content did the failure happen? And what was the values of matrix suction and hydraulic conductivity at the point of failure as per the analysis?
I haven't plotted those values, but so yeah, I didn't point out earlier, but at the time of failure, the value of suction was close to zero near the ground surface, but the suction did not quite dissipate completely when the failure occurred. So there was still some amount of suction, less than 10 kPa, but there was still some suction, so it was not fully saturated. So based on that, yeah, based on that and based on the wetting soil water tension curve, we can estimate what the volumetric water content at the time of failure was, but I haven't plotted it here. Sorry.
Okay, thank you. And the last question, probably from the question answer point here, is it's a very generic question. What is the soil model used in the Plaxis model?
So we use the Moore column model for this analysis.
Okay, thank you. Thank you very much. So if there are no other questions, can I again thank Samprada Pradhan for giving us her time and a good talk on the landside investigation schemes. So thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye-bye. Yes. So moving to the next session, again, I will thank the speakers very well that a little of time which we lost in the initial part is finally covered. Now this particular session starts right at the time it has been planned. And I would be happy to welcome Dr. Ashutosh Kumar, my colleague from IIT Mandi, to be giving a talk on the effect of environmental load on cyclic behavior of soil. So before he takes over the session, I request Aditi to introduce the speaker to the audience participants.
Now, I would like to introduce our next speaker for today, Dr. Ashutosh Kumar. Dr. Ashutosh Kumar is Assistant Professor in School of Civil Engineering at IIT Mandi. Before joining IIT Mandi, Dr. Ashutosh Kumar was working as a postdoctoral research associate at Durham University and a part-time lecturer at Teesside University in the UK. His work in Durham relates to the understanding the performance of transportation infrastructure with changing climatic conditions. He has also worked on investigating the causes of collapse of UNESCO World Heritage Sites in Nepal through a British Academy funded project. He obtained PhD degree from IIT Bombay and is recipient of IIT Bombay Best PhD Thesis Award, which was conferred by our Honorable Prime Minister. He is also a DART Fellowship awardee from Germany. He has been awarded 2019 Outstanding Reviewer Award from ASCE International Journal of Geomechanics. He was awarded an ISSNGE Student Scholarship to attend a geotechnical earthquake engineering conference in New Zealand in 2015. He served as a 2016 DART Young Ambassador for DART India. He has also been selected as an early stage researcher to attend and present his research work in the Researcher Link workshop that was organized in Brazil during September 2018, supported by Newton Fund of UK. He has published over 30 papers in various conferences and journals of international repute. I welcome you and thank you, Doctor, for your valuable time.
Okay, thank you very much, Aditi. So before I would start, most of the part, like Professor David and Dr. Aras, Dr. Samprada, they were trying to talk about the monotonic behavior of soil, and they have tried to bring the soil water retention properties and how it is important in order to interpret the strength parameters of the soil. So what I would try to touch upon is what is the impact of environmental load on the cyclic behavior of soil. So before I would go to my presentation, I would like to acknowledge the colleagues with whom I have worked, and the work which I'm presenting today, it is the part of Transport Africa project, where I was working as a research associate. So in the figure, you should be able to see Professor David Tall, Dr. Aras Azizi, and the colleagues from Ghana, as well as from Tanzania, like Professor Ampedu, Dr. Mazuma Ligwanda, Dr. Sidney Lyra, and Professor Hannes Grabe. And so all of these colleagues have helped us in this project, where we have tried to understand the behavior of soil, which is mainly present in South African or the African countries. So in today's talk, I would be discussing that why our research should incorporate environmental loading. I would be giving the brief description about the project in which I was involved, and we named it as Transport Africa. I would be discussing about the impact of drying wetting on the mechanical behavior. Firstly, under monotonic loading, then I would be discussing about the development of cyclic triaxial testing protocols and how we try to understand the impact of wetting and drying on the cyclic behavior of soil and the soil which was taken from the subgrade or the formation level of a railway material. And then I would be concluding. So one thing that is important for us to recognize is climate change. So when we talk about climate, it is nothing but the average weather in a place over many years. And what we are seeing today is there is a gradual shift which is happening in the climate, and that is what we represented as a climate change. If you recall the discussion which has happened during COP26 in Glasgow, that we must try to keep the global warming by 1.5 degrees Celsius till 2100. So climate change adaptation, if we talk about, because what we are seeing today is whatever infrastructure which we are developing, these infrastructures are going to be present tomorrow as well. And these infrastructures are going to show some performance when the climate might be different. So our strategy should be that whatever infrastructure which we are considering or which we are constructing, it should be able to perform better when the climate might be different. So our adaptation strategy must be able to take or tackle the challenges which has been brought by climate change and which is impacted and which have the impact on the performance of the infrastructure. If we look into the IPCC recommendations, then it says that the tropical countries and most importantly, the Western Africa, these are going to be the climate change hotspots. These two regions are projected to experience an unprecedented climates around 2030s to early 2040s. And this is going to be much earlier than anywhere else on the earth. And this is the temperature distribution and rainfall distribution. If you would see here, let me switch to the, yeah. So this is the distribution, and we can see very high distribution of rainfall, where you have 3,100 mm of rainfall in the mid part of Africa compared to the rest of the Africa, and the similar temperature distribution which we can see here. If you see that how these environmental load, mainly which has been brought by climate change phenomena, which is causing the extreme events of rainfall as well as the extreme drying, how it is impacting the infrastructure which we are constructing today. One of the examples that we can see here is the derailment of Kamini Express in India during 2015, and it was on the account of embankment failure. And this mainly happened because of the washing away of the ballast and the formation soil. And it was a heavy rainfall, and that heavy rainfall causes it got pounded onto the one side of the embankment, and then there was an overflow. And when the driver was approaching that region, he did not understood, or he missed it, that track was, the soil below the tracks were completely washed away. And this causes the washing or the complete derailment of the track. And it was very much detrimental, like it caused the death of around 45 passengers. Another case of derailment, if you would see here, is the derailment of a freight train at Cricklewood in UK, where there was a derailment of the train that we should be able to see. So in this case, there was a repair work which was going on, and the speed restrictions were imposed. And when they imposed the speed restrictions, so all the trains were running at the restricted speed, but one of the train, when it was carrying some of the loads, like they were carrying aggregates in them, and it was non-uniform distribution of load. What has happened during that time is there was a excessive cant which has developed because of the twist which has been brought by the movement of embankment, and that causes the derailment. But the loss of life in that case was nil. Another case that you should be able to see here is the derailment of a freight train again in 2012. So here, this is the location of derailment, and it was again brought by heavy rainfall. You should be able to see that in that region, there was a heavy rainfall and the impounding of rain that we can see over here. So this is the direction of the travel, and this is how the train got derailed. This is the much closer view of that you should be able to see. When the investigation was carried out, it was found out that there was a slipping of the soil mass which has happened here, and that has caused a vertical drop of 0.5 meter. And when the further investigation has been carried out by Rail Investigation Branch of UK, then a clear scar was seen, and it was mainly due to the ingress of water within the embankment, and that ingress of water causes a interface between two layers, and that interface is just the first one, the top one just got slipped, and this is how it looked like. So at the time of derailment, the train speed was 60 km/h, and as it was evident that one of the line just got dipped and causing the failure of the embankment. So the main cause which was ascertained was the water within the embankment. Because of the ingress of water, it reduced its stability, and that causes the failure of the embankment, or that causes the slip at the junction between the clay as well as the ash layer. So this has happened. Another case of derailment that we can see here is the derailment because of the landslide which has happened near to the Wicklow station, and this is how the picture looked like. So you could see that how the rainfall infiltration or the rainfall percolation inside the soil mass has capability to alter the natural state of the soil or the compacted state of the soil, and it can cause the huge disruption to the infrastructure that we are planning for. And if we consider the case of UK in 2015, there were 143 earthwork failures on the UK rail, which equates to more than 2 embankment failure per week. So there are various methods in order to establish the proper stability. And one of those methods is shown here, and that is what they have done later on, was the areas has been managed with the help of vegetation. So if we look into the railway infrastructure, we can see here that the entire railway infrastructure, or we could see that this is the top portion which is resting upon the ballast layer. We have sub-ballast layer and we have compacted subgrade. This particular compacted subgrade, these materials are usually present onto the site, or they have been transported from another site, and they are usually compacted with the help of rollers. So this has tendency to exhibit variations or exhibit the properties change because of the water ingress. So this is the one which our concern is, that how we can stop the ingress of water. And if I would say that we have to stop, this is very, very difficult question, that can we completely stop the ingress of water in certain kilometer of length? It is really very difficult. Or what should be our strategy so that these compacted subgrade should remain in the stage when we have compacted it. So this is the question that we have. And for that, we have to understand that how these compacted subgrades are behaving under the different conditions of moisture ingress as well as evaporation. And if it comes in contact with water, it has tendency to become mud, and then it would start flowing in the direction of least confinement, that would be towards the top surface. So if you would see this particular case where we have a stable site, then during the onset of instability, it has tendency to travel towards the zone of least confinement, and this is how it would be visible when the failure would arise. One of the techniques that we adopt in order to strengthen our infrastructure, or mainly the railway infrastructure, while we are performing the investigation, what we try to do, if we find any type of undulations or any unserviceability in the track, we try to fill the material that is ballast within this particular pots which has been created because of the softening of the subgrade soil. And this is what we usually end up into. So this, if we see here, we are excessively using the material which is non-renewable. So this poses a huge question that what should be our sustainable and resilient design strategy so that our non-renewable infrastructure resources can also be saved. This is how mud pumping usually looks like. So you should be able to see this is like covered with mud, or this is covered with dirt. You should be able to see when it dries out, it looks usually like that. If you compare here, this usually looks very fresh compared to what it is present just beside the slipper. So I will play the video, you should be able to see when the train moves, how it is behaving. You should be able to see the complete up and down movement of track in this particular region where we have mud pumping event compared to the other regions. So this causes a huge disruption, or this causes the huge stresses onto the infrastructure, which is our sleeper as well as the rails which are here, and it can even crack them. You should be able to see, I would play the video again. So you should be able to see that how these muds, these dirt, ballast, and how it is going up and down, and other portions are not doing up and down movement because of the movement of rain. This is how it looks like, and it is very, very important for us to understand. And this is one of the cases that you will observe. Another case there where the mud pumping is also evident when there is a very huge change in stiffness of the track, when the track is approaching any tunnel or if the track is approaching any bridge. So in that case, it is changing its stiffness from soil to the deck, which is made up of concrete, and it is causing the huge variation in stiffness. And this kind of phenomena is evident over there. So in addition to the problem which has been brought by the environment, we can see that the problem which we are also building up here because of changing the stiffness of the track, we have the problem of mud pumping that is evident. If you will see the transportation infrastructure mainly in African countries, so like all other countries, they have railways and road network. So in railways, I will be discussing about the railways, that how we are trying to understand and investigate the properties of subgrade or formation soil. I would like to highlight that one of the typical transportation infrastructure which is used in rural part of the African countries is low volume road. It carries around 90% of the traffic volume, and it is more than 1,700 kilometers of road within the rural part. So it is very, very important, and it is very much detrimental if it is exposed to the extreme weather condition which is brought by the extreme rainfall or extreme drought condition. So as I tried to say, that it constitutes a major proportion of road network in Africa, providing the only form of access to the rural communities, and the livelihood are mainly dependent on the accessibility of these roads. So it is essential to improve, and if we are looking towards improving the rural livelihoods, then we have to see that how these low volume roads should be improved. So there are 4 parameters when we talk about sustainability, and one of them that is important for us is how we can make infrastructure environmentally sustainable. And as it has been suggested by Chinoski et al. 2013, that upon 2100, it will cost African continent around $183.6 billion to maintain and repair roads damaged from temperature and rainfall changes due to the climate change event. So we must adapt a strategy that should recognize the climate change in our design process. So we have to develop the understanding of the material itself, as Professor David was showing the result of the testing which his team and he has carried out for the materials from Kenya, for the materials, and Aras was also trying to show the result from the materials from Ghana. So I would also like to show some of the result that we have tested in the laboratory at Durham University, and what we have tried to understand that how these materials are behaving. And once we develop the understanding that how these materials are responding when it is subjected to extreme weather event, which can be simulated in the lab by subjecting it to the drying and wetting cycles, then only we should be able to modify the materials to suit the specification. One of the concern that would be that why we cannot use the standard material. So it is very, very difficult to get the standard material, and we have to transport that standard material to the site, and it would cost a lot of money. Considering the requirements that we have and considering the economy that Africa faces, it is certainly we specified that how the infrastructure that we are developing, it should take care of the local availability of the material, and we should use that available material in a way that it should be used. So when we talk about these things, and of course it has been brought earlier by other speakers that we have drying and wetting cycles that is brought by evaporation and precipitation event, then our infrastructure or the material itself should be resilient in order to respond to this particular event of hydraulic loading. So it would require the understanding of how these materials are degrading under the different conditions of environmental loading. So as we understand that our infrastructure is continuously interacting with the environment, which is posing the heat migration, which is posing the water migration in and out. So we should consider these effects as well. For the time being, we have not considered the heat migration within the soil mass. We have just considered how the water is ingressing and ingressing within the soil mass. So if you look into why there is a disjoint between the requirements of specification of construction material and the observed performance, it is mainly because we have the insufficient knowledge of the fundamental behavior of construction materials in tropical climatic condition, I must say. And one of the picture that Aras was showing from Game of Thrones. So that is the main thing that we could see, that we have so much of people in our area who are working in the area of unsaturated soil mechanics, area of saturated soil mechanics, but very few people are working in the area of unsaturated soil mechanics, which is the condition that is existing in the field. And saturated soil mechanics is just one condition which is fulfilling for the unsaturated soil mechanics when the voids are completely filled up with water. So our materials are mainly unsaturated. So the principle of unsaturated soil mechanics should be applied for the design. And for that, we should have the understanding of hydraulic and mechanical behavior. We should have the understanding of how these materials are behaving under the hysteretic nature of soil and suction and moisture relationship, which has already been discussed, and it has been brought to the on this platform. So when we see that unsaturated soil, we have an ingress of water. What we usually see, there is a reduction in soil suction, there is an increment in the volume of the soil, and that has tendency to increase the soil pore pressure, that has tendency to reduce the strength, which ultimately causes failure. So our design processor should try to incorporate these events and how these events is leading towards failure that we have to bring. And this is the typical curve which is trying to bring that at a certain value of water content, we have different value of suction, and that different value of suction will be governed by how many cycles of loading and unloading has been brought onto certain material which is compacted in nature. And this would have tendency to dictate the shear strength of the soil mass. So to address the global challenge of providing a sustainable and resilient infrastructure in Transport Africa project, we tried to understand the sustainable construction materials, and which is locally occurring for the roads as well as railways. We tried to understand that how bringing the different events like wetting and drying, how it has tendency to change the shear strength of the soil mass or the evolution of pores within the soil mass. A key common element was measurement of suction in laboratory as well as during the field monitoring. So first I would try to explain that what we have understood by investigating the road materials from Tanzania. We try to understand when we are trying to apply the hydraulic loading in form of drying and wetting cycles, how the material has tendency to respond. And for that, we transported the materials from Tanzania to Durham University, UK, and then we prepared a soil sample of triaxial soil sample, cylindrical in nature, of 38 mm diameter and 76 mm in height. And then we subjected these soil samples to different conditions of drying and wetting. Drying is carried out in the laboratory environment, where we just expose it to the atmosphere and then we just dried the soil sample. And we continuously monitored the loss of weight of the soil mass as well as the volume using the digital caliper. To wet the soil mass, we have kept it within a fogger where the relative dense humidity was maintained around 100%, where the samples would observe the moisture and it would have tendency to gain the moisture. And during that time, while it is gaining the moisture, we tracked the volume change as well. So this is the typical response that we got. Like we prepared the soil sample at optimum water content and then we subjected it to the atmospheric drying. And this is how it has come to its residual water content, and then it has tried to increase and during the wetting process that we did in the fogger or in the humidity chamber that we have developed. During that time, we tried to obtain the volumetric strain that the sample has exhibited upon the water fluctuation. So this is without any load. We have just tried to understand that how sample is behaving when it is just subjected to hydraulic loading. One thing that you should be able to see here, that it has undergone the irreversible volume change behavior, that it has started from 0% and it has gone to -7%, and once it is wetted, it has gone to 2.5% of volume increment. If we would keep all the results here for 6 cycles of wetting and drying, which we have subjected it to, what does it mean? That we have 17 or 18 samples and we subjected each samples to the different cycles of drying and wetting, and we tested under the constant water content condition. But what we can see here for the 2 samples, what is kept here is once it is subjected to different cycles of wetting and drying, during the initial cycles, it has shown increment in the volume and reduction in the volume, but after few cycles, it has just got stabilized. The volumetric strain is getting stabilized. This is showing that the sample would show, the compacted soil would have tendency to show incremental volumetric strain during the first few cycles, and that is mainly due to the evolution of pores providing the preferential path of the water, development of microcracks, and after few cycles, when these microcracks would get stabilized, it would have tendency to show this constant value or constant or stabilized volumetric strain. So this is the response that we have got from the laboratory. Then we performed different testing, like we just performed constant water content testing onto the samples, and those samples were subjected to first drying, first wetting cycles, third drying, third wetting cycles, 6 drying and 6 wetting cycles. What does first wetting mean is we prepare the soil sample at optimum water content, we completely dried it up to the residual water content, and then we started wetting it using this particular fogger or humidity chamber that you are able to see. And then we reached it up to certain value of water content. And then we have tested it under the constant water content condition in the triaxial sample apparatus. One thing that we can see, that development of crack here onto the sample, and these micro cracks, we are able to see the cracks which is present onto the top or which is visible onto the top. There must be many cracks which is inside the specimen, and it would have impact onto the strength properties of the soil that we try to understand. So this is the typical axial stress versus axial strain response that you are able to see. So once we are trying to reduce the water content, that means we are going towards drying the soil sample, we can see that there is an increment in the strength. This is mainly because of the increment in the soil suction that we are able to see here, that the suction is increased from 2.74 MPa to 16.1 MPa. And these suctions which we have measured, of course, the tensiometer which has been developed at Durham University has capability to measure suction up to a range of 2 MPa. So we have done this measurement in dew point potentiometer, and we have measured total suction here. And one thing that you should be able to see here is once the suction is going towards higher level, the soil has tendency to show brittle behavior, and it would show direct peak without like upon the failure. So this is how the sample have tendency to behave. When the sample is subjected to different cycles of drying and wetting, and when we are trying to apply the deviatoric stress onto the sample, this is the way the excess stress versus excess strain would look like. And you should be able to see that at certain value, when we talk about 6 wetting and drying, even though we had the higher level of soil suction, the strength in 6 wetting is less than the strength during the drying. So this can be captured using by bringing the coupled nature of soil water retention behavior. One important characteristics that we can observe here, that when we plot it with respect to axial stress at failure with respect to water path, then we can see here for the result of as compacted, first drying, first wetting, third drying, third wetting, 6 drying and 6 wetting, we should be able to see that once the suction has increased, the excess stress at failure has increased. But when we are going towards higher level of hydraulic loading, we should be able to see that at 6 wetting, even though we have higher level of suction, we have reduced strength. This has been brought mainly by the development of crack which has happened, and the suction which we are monitoring is the global suction, is the local suction. It is not the global or entire suction. We have taken this one of the small portion of the sample and we have kept within the WP4C in order to monitor what is the suction level. So the crack propagation which is happening and the crack development which is happening when we are progressing towards hydraulic loading, only suction cannot predict the entire behavior. We must have understanding that how these cracks are propagating and how these cracks coupled with the suction can control the strength parameters of the soil when it is compacted and when it is subjected to loading. Same thing can be seen when we try to plot it under the different conditions of wetting and drying and wetting. This is the result for first drying that you should be able to see. And once we progress with the wetting and drying path, this is the result that you should be able to see here, that the result is at a certain water content, you have reduced value of axial stress when it is subjected to different wetting and drying path. This is how the similar result we have also seen in the case of Young's modulus, and this is how it explains the importance of wetting, drying, as well as the development of crack within the soil mass, which have tendency to dictate the engineering behavior of soil. Coming to the railway project that we tried to do, so this is the, is there anything? Sorry, I will just
creating a problem there.
Okay,
Just take it out.
this one?
What?
Yeah,
No. Perfect.
yeah, all right. Okay, yeah, it should be okay. Yeah, I think it should be okay. Thank you, Dr. Uday. So this was the monotonic testing that we did, and that was the observation that we have made from the monotonic triaxial testing. Then coming to the project that we did for the South African coal line. So here we tried to understand the impact of soil atmosphere interaction, and when it is coupled with the railway the mechanical behavior of the embankment with changing environmental condition. Idea was how we can predict the design life under the changing environmental load. And for that, we conducted field measurements. So we had the site in Blaubank, and we had site in Durban. So we visited the site, and we had the sensors installed in the site. We performed laboratory testing at Durham based on the soil we received from South Africa. Then we performed numerical simulation over them with an overall objective is how we can mitigate the climate risk at the design stage. So this particular line is very much, or strategically, I would say, very much important for South Africa, as it connects 40 coal fields, and it connects directly to the Ricard Bay coal terminal. So it is very much important for the economy of South Africa. When it got constructed, a lot of investigation has been done, and there are many cases of its repair, and a lot of research has been done even by the research group of University of Southampton. So we also try to understand that how these materials are and how these materials are going to respond when it is subjected to coupled nature of hydraulic loading, as well as the load which is coming due to the movement of wheels. So that is the mechanical part of the loading. So it is 650-kilometer long South African coal line. And this is the typical arrangement of the embankment, where we have the ballast, and below that ballast there is a special sub-ballast, class A subgrade and class B. So we try to test this class B subgrade layers, and these specifications is given by Transnet. Transnet is an agency which is responsible for maintaining and operating these railway infrastructure. These trains are mainly running at the speed of 50 to 80 kilometers per hour, and it is heavy hauled line, actually, having the axle load of 26 ton per axle, actually, and it is very, very long, like it will be more than 2 kilometer long train. So these are very, very important, and these trains are run by the 5 engines. So it is they are very heavy, and it impart a lot of stresses onto the ground or onto the railway substructure. So once we see the load distributions that it usually get at this particular level of subgrade, the stresses are mainly around 40 to 60 kilopascals, and we try to apply that in our laboratory testing that I will be showing. So we try to perform cyclic triaxial testing with an idea to understand what is the influence of coupled hydraulic and dynamic loading onto the performance of the materials that we have been testing. Then the influence of loading cycles on the train speed and the train speed. Then the impact of drying and wetting cycles onto the subgrade performance. And while doing that, we were continuously monitoring suction as well as pore pressure. We also try to understand the influence of drainage conditions and the influence of dynamic hydraulic loading, as I was telling in the first case, where we try to apply this atmospheric drying in the atmosphere, as well as the wetting we were trying to apply. So we try to understand the impact of that as well. And for that, overall aim was to understand the stiffness, understand the resiliency and the resistance to permanent deformation, which would help us to understand the stability of this particular soil and when it is subjected to the coupled environmental as well as cyclic loading brought by the train movement. So we developed different testing protocols. First, we tried to understand the saturated samples under free to drain conditions. So this condition would give us an idea that how this particular soil is going to respond when it is completely saturated. And that condition would be free to drain condition. So these conditions we have designed in our triaxial setup. Another condition would be that testing unsaturated samples under the constant water content condition, and those samples we exposed it to different cycles of drying and wetting when it was kept outside before assembling it into the triaxial setup. And then we applied successive cycles of cyclic loading, and we also wetted the sample. So that would be the staged condition of wetting as well as cyclic loading. So this would simulate a condition when there is a rainfall onto the embankment, there is a water percolation inside. At the same time, we have the train moving. So these kinds of testing protocols we have designed and we have executed during the cyclic triaxial testing. This is the example of the wetting that you should be able to see. So this is the triaxial sample of dimension 70 mm in diameter and 140 mm in height. And this is how we have wetted the sample. So you should be able to see the fog here, and this was wetting our soil samples, and we have continuously monitored the wetting. We have continuously monitored any volume change during this process. The soil we got was, or which is present at the site, was clay sand. This is the typical property of that this particular material, and this is the view of the sample. In order to understand that how the volume change is happening within the soil during the cyclic testing stages, we have these local instrumentations in order to obtain the radial strain, in order to obtain the axial strain, and that would give us the volumetric strain, what is happening. So we tried to obtain that at the mid height of the soil sample, which is the zone of maximum shearing. So this would provide an idea about how the void ratio during the different stages of cyclic triaxial testing is changing. At the same time, we have monitored suction continuously during the cyclic stages. So this has given an idea about the dynamic nature of water retention path that we can directly keep within the soil water retention curve that was discussed by Professor David and highlighted by Aras as well. So this is the more closed view of the tensiometer, and you should be able to see that we have glued the tensiometer here, and it has been inserted by cutting a hole here, and then we have sealed this so that there should not be any water exchange between the sample as well as the water present within the cylindrical cell. And this is another view of that. So this is the triaxial setup that we have used for understanding, which has capability to apply up to 5 hertz of cyclic load. And this is how it looks like. So one of the most important part for us to understand the water retention behavior, and again for that we have used the water retention testing setup developed at Durham University. And this particular setup has helped us in understanding that hysteretic nature of this particular soil mass, where we can see that this is the drying curve. I will just bring that. So this is the drying curve where it is meeting around 200 kPa. It is meeting at main portion of the drying curve. This would be the scanning portion of the drying curve, and then we tested up to 600 kPa, and then we went towards wetting the soil sample. So we had continuous measurement of wetting and drying, and then we also had the discrete measurements in order to obtain the parameters for Van Ganuten model, which has been used later on in order to develop the prediction of the behavior of the response that we obtained from cyclic triaxial testing. So these are the test samples that we have tested, where we had as compacted specimens. So we had 3 as compacted specimens. We subjected the soil to first drying, first wetting, and then third drying and wetting phenomena. So these are the locations where these are the water retention states of these soil samples. You should be able to see here the water retention state for first wetting, second wetting, and third wetting samples. So it is lying just onto the wetting path. This is mainly because we completely air dried the soil sample and then we started wetting, and that is the reason they have located onto this particular line. Once we prepared the soil sample, we wrapped the soil sample and then we kept it for 25 hours, or once the sample was ready after hydraulic loading, we wrapped it for 24 hours for water homogenization. And then we arranged the soil sample onto the triaxial pedestal. And then we attached the tensiometer, and this is how the suction equilibrium would look like, and this is how we received the suction equilibrium. So the constant value of suction equilibrium guided us in saying that, okay, the equilibrium value of suction is achieved, or the sample is at equilibrium suction. We can go for the further stages of cyclic triaxial testing, that is compression stage, and once compression is complete, then we can go for shearing stages. So these are few fluctuations that you should be able to see. That fluctuation we got because we were continuously applying silica gel, so that there should not be any ingress of water between the cylinder of the double cell wall cylinder, or the water which is present for testing, and the soil sample. So this is how we have tested under the different condition of water content fluctuation under the different stages of wetting and drying. So as I told that we have tried to perform a couple of different testing which would have tendency to showcase what is exactly happening in the field when it is completely saturated, when it is having constant water content, or when it is subjected to the packets of cyclic load as well as wetting. These are the typical applied deviatoric stress response for 40 kPa. One thing that we always try to maintain is 10 kPa of resting stress while the deviatoric stress were applied. So this was mainly due to make possible contact between the loading ramp to the sample during the testing, and also to have the load of the track as well as the sleepers, and in order to simulate that condition, we have applied the resting stress of 10 kPa. So we have tested under the different conditions, and here you should be able to see the cyclic stress of 40 kPa as well as cyclic stress of 80 kPa, where the confining stress of 20 kPa was applied, that is representative of the confinement that would exist into the railway embankment. Under the consolidation stage, that you should be able to see that once we applied consolidation or confining pressure, the suction has just reduced and it has gradually attained a certain value. This reduction is mainly due to the volumetric compression, and that volumetric compression would have tendency to increase the degree of saturation, and that can eventually reduce suction, and this is what we have seen here. But this initial reduction that we are able to see, this is because of the local overpressurization of the tensiometer that has happened, or the soil paste that we have applied over there, and that has created this quick reduction, and then we have gradual reduction. So once we have equalized suction reading has been obtained after the compression stage, then we proceeded for cyclic stage. These are the typical result for axial strain. As I was showing you that we have used local instrumentation to measure. So there were two local or axial LVDTs that were present to monitor the axial strain. Then there was one radial strain that helped us to obtain volumetric strain. From that, eventually we got the degree of saturation based on the constant value of water content or water content that we were continuously monitoring. So we had the measurement of volumetric strain, we had the measurement of suction. That helped us to understand the dynamic nature of water retention. Another important testing procedure that we applied is we tried to understand that how the sample is behaving under the different speeds where we have a resting period. Of course, when the train is passing, some train would be passing at restricted speed, some train would be passing at normal operating speed, and that we have fixed as the requirement of the configuration which is given in Transnet guideline. We have done that. So this is 40 km/h. We have applied after rest period, we have applied 80 km/h, and then we have gone for applying 160 km/h. And in order to understand how the suction as well as degree of saturation is changing and how the axial deformation is there, and then we can understand the resilient modulus or resilient behavior of soil. So this is the typical loading application that you can see here, where you have 1,000 cycles of 1 Hertz, you have 1,000 cycles of 2 Hertz, you have 1,000 cycles of 4 Hertz, replicating the three conditions of restricted speed, normal operating speed, and high speed. In between, we have a rest period. So this is how the axial strain got developed within the soil mass with increment in the frequency. We always observe the development of higher strain level. This is mainly because of the higher dynamic stresses which is getting applied with the increased train speed. When we try to plot the result, this is the result for not for the successive loading that we have applied. This is the result for the individual loading that we have applied for the train which is running at 0.5 Hertz frequency, 1 Hertz frequency, 2 Hertz, and 4 Hertz frequency. When we see the result for the successive load that we have applied, we can see that maximum loading or maximum strain which is coming up is during the first cycle or during the first stages of the loading that we have applied, and after that we received the more or less the constant value. This is mainly because the sample has tendency to become resilient after application of few cycles or few hundred cycles of cyclic loading. And if you see the deformation, how it has reduced, so maximum deformations of around like 80% deformations have been received under the first cycles or 1 Hertz of loading, and then the lesser and lesser deformations is received. This is the response of suction which we have got under the different cycles, and this is the response for the degree of saturation that we have received. We also tested the soil sample under undrained testing condition. Under the undrained testing condition, when we do not allow sample to dissipate pore pressure, so there would be a development of pore pressure, and this is how sample has accumulated the pore pressure during the first 1,000 cycles of loading, and this is how the pore pressure development is plotted. And then we have a rest period. Once the rest period is there, then we allow the water to dissipate, and this is how the sample dissipated the water. And then again we applied the 1,000 cycles. We again having the rest period, we again apply the 1,000 cycle. So for all of these mechanism, we try to understand what is the response of the soil sample in form of the maximum strain that it is exhibiting under the different condition of loading. Then we had the condition where we allowed water to drain out during the cyclic triaxial testing condition or during shearing condition. And during the shearing condition, when we are allowing the water to drain out, you should be able to see there is a just increment in the water pressure, and then there is a decrement. So this initial increment which has happened because of the permeability of the water, which has led to the increment in the pore pressure, and as it has the water to drain out, or it has voids to drain out, it has just drained and it has reduced to very, very small or negligible value of excess pore water pressure. We should be able to see how suction is changing during that time. So for unsaturated condition, of course, this top result is for saturated condition, where we have also compared the result with the conventional pore pressure transducers, which is available in the triaxial apparatus, where it is measuring from the bottom. It is measuring pore pressure at the bottom, but we are measuring at both the places in these conditions, at the bottom, at the mid height of the soil sample. And this is how the distribution looked like. For the distribution of suction, this is the distribution would look like. So during the initial condition, we should be able to see that there is a gradual reduction in the suction, which is because of the compressive volumetric strain, and that compressive volumetric strain increased the degree of saturation because of the reduction in the void ratio, and that has led to the reduction in suction, and this can be predicted onto the soil water retention curve. And if we see how the samples having higher size have higher suction have behaved compared to the sample having lower suction, we can see that delayed equalization of suction can be seen, and which is usually achieved after 700 to 800 cycles of cyclic loading, compared to very early equalization of suction if the level of suction is 21 kPa. So this is mainly because of the lower permeability of the soil, as it was highlighted by Samprada, highlighted by Aras, and of course by Professor Tall, that how the sample would have very, very low permeability at very, very higher level of suction. And this is what is evident even during the cyclic triaxial testing. So when we plot this result at on soil water retention curve, this is how the path it has traced, and it has tendency to move and follow the wetting curve, and this is how it is moving. And this is what we should be able to capture here onto the suction variation. When we subjected soil sample to different condition of staged wetting as well as cyclic loading, as I was telling, that we have a condition which can be evident in the field where we have continuous wetting which is happening because of rainfall, and then we have cyclic loading because of the movement of train. So we try to simulate that particular condition where this is the result that you are saying, because this is the increment in the degree of saturation that you are able to see. This is because of the cyclic loading, and then we have wetting that you should be able to see here. This wetting, after the application of cyclic load, we injected water from the top to the soil mass, and then we wetted until it gets equalized. And so for each of these stages, we waited for 1 day, and then we monitored suction. We only started shearing when we have an equal value, or when we have an equalized value of suction. This is the response that we have achieved or we have received in terms of suction response. And this has helped us in understanding and interpreting how the stress path would move when we are plotting, and this has given us an idea to understand the movement of the stresses onto the QP plot or QP space. So if you would see the result of first cycle of cyclic load, this is where it is located. When it is subjected to 100 cycles where there was an increment in the pore water pressure, it has the stress path has moved towards left, and then once the water got dissipated, the stress path has moved again towards right. So this is the natural condition that we have tried to replicate over here. When we try to show that how it is behaving under the different conditions, like a constant water content condition, when we have very low value of suction, it is just lying onto the same path, because the reduction in suction is very, very small, as we can understand from SWRC curve, which is logarithmic in nature, and at low level of suction, the reduction would be very, very small, even with the higher increment in the degree of saturation, which is not the case when it is having the lower degree of saturation and higher level of suction. And this is what it has been seen, that we can see that higher increment in the stress path, or the decrement in the stresses or mean bits of stress that we can see here. So all of these tests, when we try to plot here, this is the critical state line that has been given by Grabe and Clayton in 2009 geotechnique paper. So we have I think it is Journal of Geotechnical and Geoenvironmental Engineering paper. So when we try to keep this particular result on deviated stress versus mean stress plot, so this is how the stress path looked like, and this has helped to understand that how it is moving when it is subjected to the different stresses or different conditions of degree of saturation. And with that, we got the various we got to develop the mathematical model that has capability to predict the strains and resilient modulus within the soil mass. And as Aras was trying to bring out that only Bishop stress cannot predict the behavior, so we have tried to bring the bonding parameters given by Gallipoli, and these bonding parameters can, along with the Bishop stress, can help us, and it helped us in order to predict the resilient modulus of the soil mass under the different conditions of drying and wetting. Because you should be able to see here under the wetting conditions, it is the suction is increasing. Under the drying condition, the suction is decreasing, as well as under the same condition of suction or the same value of suction, there were different values of resilient modulus. So only suction was not sufficient enough in order to predict the behavior of the resilient modulus of the soil or the axial strain of the soil. And for that, we can see that from here, as Aras was trying to bring out that as well. As you can see that the values are scattered over here, and one line cannot bring out what exactly is happening, because we have to bring another parameter, that is bonding parameter. And if you should be able to see bonding, if it is 0.32, it is showing higher level of axial strain, and if it is lesser, if it is showing like 0.62 value of bonding parameter. And if we have to predict, then we have to develop a model that should be able to capture, and that can be captured using the bonding parameter as well as bringing suction together. So this is how the model looked like. And this is how we have tried to bring, depending upon the axial strain and resilient modulus. How much time I have? Okay, so I think I am at the end of the time. So we have tried to understand the resilient modulus as well as the axial strain. So this is how the properties are, and we were able to understand this based on the prediction model that we developed that has capability to predict in terms of Bishop stress ratio as well as the bonding parameters. So what I would try to say in conclusion is the moisture content, degree of saturation, density, these are changing because of the environmental load, and it has significant influence onto the deformation, strength, stiffness, as well as the tensile strength properties, which have tendency to develop crack, and it must be accounted while interpreting the result for unsaturated soil behavior. The setup we developed and the local measurement of suction that we did using the high capacity tensiometer as well as the volume measurement at the mid height, it helped us to understand that how suction as well as degree of saturation is changing and how it has tendency to dictate the water retention behavior or the stiffness and strength parameters of the soil. So with this, we try to understand the dynamic nature of railway formation soil, which have the coupled impact of train-induced cyclic load as well as environmental load. So at the end, I would try to say that research and collaboration among stakeholders to incorporate climate change adaptation strategies is the way forward in our profession. Thank you very much. If there is any question, I'd be very happy to take. And I'm very sorry if I have taken and if I've exceeded the time which have given to me.
Thank you very much, Ashutosh. It was good hearing from you on basically you started very well with the case studies and basically the need of why we should be doing all the necessary investigation to exploration to computation, whichever you assured it very properly in your presentation, and we thank you for the extensive presentation. Now, should I quickly ask for 1 or 2 questions from the participants or audience, if there are any?
Throughout the year, we have many seasons like winter and summer. So, what is the effect of the rate of drying and wetting on the properties of soil?
Well, so again, the question would go same as Dr. Uday was asking, that what is the impact of the rate of evaporation as well as precipitation. So of course, it has a good impact. If you have higher rate of evaporation or higher rate of wetting, then it would have tendency, either the soil, if there is a preferential crack, or if there is a crack, then of course it would add more of water to it. If not, then water would just certainly pass out. So if there is a crack in there, so definitely it would fill with a different higher rate within the soil mass, and of course it would deteriorate the soil very quickly. So higher rate, the cloudburst phenomena or very excessive drought phenomena. So of course it would have very great impact, but our study, we have not brought the rate yet. We have tried to just understand is how at a certain rate, when we are allowing water to ingress into, how it is impacting the material that we are trying to understand.
Okay, thank you for the answer. So it seems there are no more questions. So again, I thank you, Ashutosh, for enlightening us on this particular aspect. So now we'll have to move to the next presentation. So we already have the speaker here, Professor D.N. Singh from IIT Bombay. So it's a pleasure to hear from him on the topic related to the choice of suction measurements for multi-phase geomaterials and what is the way forward from this. So I request Aditi to quickly introduce the speaker.
Now, I would like to introduce and welcome our last speaker for today, Professor D.N. Singh. Professor D.N. Singh is the Institute Chair Professor in the Department of Civil Engineering at IIT Bombay. He obtained his bachelor's, master's, and doctoral degrees from IIT Kanpur. His teaching, research, and development activities are in quite diversified areas of geotechnical engineering. He has also been actively involved in various prestigious sponsored projects and published over 320 technical articles, supervised 40 doctoral dissertations, and 35 master theses. He has been successful in filing 34 patents, out of which 15 patents and 2 copyrights have been granted. Dr. Singh is the founder and editor-in-chief of Environmental Geotechniques, ICE Publishing, London, UK. He has been editorial board member of several journals of repute. He is the recipient of Young Teachers Award instituted by the AICTE New Delhi and Junior Senior Paper Award from IACMAG for the year 2005. He was chairman of 12th IACMAG Goa, India from 1st October 2008 to 6th October 2008. He is the recipient of various prestigious awards like Excellent Contributions Award 2008, John R. Brooker Excellence Award 2011, Penman Prize 2014 for the best paper published by ICE Journal, and Canadian Geotechnical Journal Friedland Award 2019 for the paper with highest number of citations among all those published by the journal in previous 5 years. Dr. Singh is fellow of Indian National Academy of Engineering, New Delhi, American Society of Civil Engineers, and Institution of Civil Engineers, ICE London, UK. I welcome you, Professor, and thank you for your valuable time.
Thank you very much. I hope I am audible and you can see my slides, the first slide on the screen.
Yes, very much.
Yes, sir. Yes, sir.
Thank you. Thank you very much, organizers, for giving me this opportunity to speak out my heartfelt feelings on this very important topic, which I have been pursuing since almost 2 decades. And the credit goes to Professor Digitol, who has been helping me in the initial phases of my research. Professor Friedland and Professor Toll are the two gigantic personalities who have been contributing to the subject immensely, and our generation has learned from them. I'm going to be a bit philosophical in today's talk because everybody talks about the suction measurements. And in fact, truly speaking, when you deal with the multi-phase geomaterials, then suction measurement becomes a very big challenge. And that's what the theme of my discussion is. So what should be the way forward and how we should be dealing with it? I have taken liberty of switching over from soils to geomaterials because in the contemporary geotechnical engineering and the environmental geotechnology, which I am trying to learn, soils have got transformed from the naturally occurring material to the anthropogenically occurring materials, and hence I use the term geomaterials rather than the soils. I am DN Singh from IIT Bombay, and I belong to Department of Civil Engineering, Geotechnical Engineering Division. And once again, thank you very much, Professor Ashutosh Kumar and Professor Uday Kala and the other organizers for giving me this opportunity to speak on the subject. So I'm sure by the end of the day, it's very clear that what is the difference between saturated versus unsaturated state of the geomaterials. As I said, geomaterials is the word which I'm using for the soils, and in particular, the man-made soils or the synthetic soils. And because I work in this area, I use geomaterials as a synonym for man-made soils. So the basic difference is that pores in the soils are filled in with air and water in the case of saturated material. So if you consider the basic model, we have soil particles and the water. This is what the saturated state of the material is. However, if air intrudes into it, it becomes unsaturated. And this is where we bring in the concept of how air, water, soil, minerals interaction is going to take place. And this interaction causes soil suction to develop. And that's what actually we are trying to measure, quantify, so that we can master the unsaturated state of the geomaterials, be it their compressibility, permeability, shear strength, heat migration, or whatever. So truly speaking, all these characteristics of geomaterial are going to be strongly linked with their suction. And this suction itself is linked with the moisture content. So if you want to understand the geomechanical properties or characteristics of the geomaterials, if I measure the suction, which is a function of moisture content, I can champion how this material is going to behave. And all of us know that what are the parameters that influence soil suction. The first one is the soil type, what type of soil you are going to deal with. Particularly whether it is organic matter or it's a inorganic matter rich soil, what are the particle size, pore size characteristics, temperature. Then we talk about the dissolved salts or the pore solution, which makes the soil what it is. Then of course the grain structure or the morphology of the soil, compacted state of the soil, which is going to directly influence the pore size, water content, and history of drying and wetting. Professor Ashutosh Kumar was talking about the drying and wetting. Now, for a time being, if I ask a question that suppose if this soil has enough organic matter, which is liable to decay, all right? So from this point onwards, the shift in the suction measurement starts. That means we are dealing with a soil mass or the geomaterial, which is not going to be a control volume as a function of time. So this is where the first question mark is. The second question mark is the particle size and the pore size characteristics might be changing with time. How it is going to happen? Subsequently, I'll be talking about how multi-phase occurs or gets initiated into the geomaterials. So meaning thereby, the pore size and the particle size may not remain constant all throughout. One good example would be precipitation or microbial activity. All right, so the pores are getting clogged, the particles are either growing or there could be a dissolution and hence the particles are decreasing. So truly speaking, the pore size and particle size is not going to be constant. We talk about the temperature, but what about the pressure? I'll give you ample example by the end of this talk, where the pressure is going to control the basic behavior of the geomaterials. And of course, the dissolved salts. So this is what I was talking about earlier, that the pore solution characteristics are going to depend upon the dissolution of gases. once the disintegration or the decay of the organic matter which is present in the soil starts or the geomaterial starts, this gas formation would take place, and then the chances are under very high pressure, the gases might get dissolved into the pore solution. There could be a mineralization also, and that is what is going to change the dissolved salts characteristics or the pore solution characteristics over a period of time. So in today's practice of geotechnical engineering, particularly those of you who are into environmental geotechnology, would be asking these questions. Similarly, grain structure or the morphology of the soil might not remain constant. This would change the moment we talk about the dissolution of the grains or because of the formation of some salts or deposition of some salts on the grains. So this becomes a dynamic system. Water content itself might change over a period of time. When the decay of the matter starts or it happens, the water is going to be consumed. The pore solution from the soil mass or the geomaterials is going to be consumed. That means the water content cannot remain constant. So the issue is when all these properties are not going to remain constant, there is something which rings the bell in the mind that how the suction is going to be measured, how the suction would be utilized to model the characteristics of the geomaterials. So just to begin with, I started my studies on soil suction measurement since 2002 onwards, to be precise. And to begin with, I was playing with the insertion tensiometers with limited capacity of suction measurement up to 80 kPa. Now these are all historic, and we used to use this data generated from here to develop the soil water characteristic curve, and from there we could obtain the unsaturated hydraulic conductivity. So there was a time when most of the research was being done with the help of the insertion tensiometers. But of course, the limitation was that these were only up to valid up to 80 kPa, and that was the biggest limitation of these studies. We used TDR probes, that is time domain reflectometry probes, along with the insertion tensiometers to compute the volumetric moisture content and the suction, and hence once you have volumetric moisture content and suction, you can develop the soil water characteristic curve. So these were all initial studies. We switched over to the pressure plate apparatus, indigenously made, where we applied enough pressure to squeeze out water from the soil sample, and online monitoring was done of the volumetric moisture of the sample with the help of a TDR probe which was connected to the soil sample. And if you take a closer look of this is how it looks like. We have a pressure chamber in which the compressed air can be filled in, and this compressed air, it is believed that would be squeezing the sample and hence would be squeezing out the water from the sample, and you can measure the moisture content which can be directly related with the pressure applied, and this pressure could be considered as the suction pressure. We moved on to suction measurement by using WP4, that is a psychrometer, or we call them as dew point potentiometer. Just now, Professor Ashutosh Kumar was talking about utilization of dew point potentiometer, and sometimes we also call this as a chilled mirror technology, and we can measure suctions up to the order of 80 MPa. The basic premise remains same, that if I can measure the suction, the total suction, I can establish the soil water characteristic curve. So most of the studies in my research group, starting from 2002 to 2006 to 10, were basically dealing with these instruments, which are now become quite, historic. Then Professor Hanumantrao, my student, he started working on something which is what is known as the influence of the energy field, and by using energy field, how we can create a state of the material which would be unsaturated. So one philosophy was to expose the sample to the thermal flux. So what you are seeing over here is we have a control volume of the soil mass which is saturated to begin with. we have a thermal probe, and using this thermal probe, we apply thermal flux on the soil sample, and then we enhance the radial drainage. And you will look that you'll find that there are some electrodes which are embedded on the top plate and the bottom plate. So we were measuring the electrical response of the soil. So the philosophy is, when you apply thermal flux, the moisture will move out, and once the moisture moves out, the resistivity of the sample is going to increase. So we did a lot of experiments by using these type of simple setups, and we could show that how temperature can be utilized for creating a state of the material which is unsaturated. So from this point onwards, we also moved on to centrifugation. That means if I take a sample of soil which is saturated, and if I centrifuge it, and if I measure the electrical impedance across different points, so suppose if this is the center of rotation, and if I am putting this sample into the centrifuge, in a spinning centrifuge, I can create a suction profile from top to bottom, and I will allow water to drain out from the bottom, and hence I can measure the electrical properties, and these electrical properties can again be linked with the suction of the soils. So this work was also done by Professor Hanumant Rao. He also was instrumental in developing this setup, a very clever way of doing things, where we utilized PME and online measurements we were doing by using the electrical impedance spectroscopy. This is a ring in which the sample has been contained, and this ring is kept in the pressure membrane extractor. So online measurements can be done to see how current and voltage across the electrode pairs is changing, and this can be ascribed to the moisture change, and moisture change is nothing but change in the suction value. So these type of simple devices we could develop, and we could show that how soils in their unsaturated state can be created. Subsequently, I shifted my interest in the field of bio-geo-interface, very relevant to the talk and the topic of this workshop, where you are talking about how the bio effects are going to influence the suctions which develop in the soil mass. And to simplify this bio-geo-interface, when you see a micrograph of the soil mass, you will realize that there are few bacterial cells or the microorganisms which are present in the soil, and there might be some bridges also between the soils and the soil particles. So these are the interfaces which we are talking about. In conventional geomechanics, normally the tendency is to not consider the bio effects which are persisting in the soil mass. Now, if you look at this, you will find that there is a geomaterial, and then there is a bio-geo interface which is getting linked over in the form of a net or a biofilm. So to me, this is a contact mechanism problem, and which might result in upgradation of the geomaterial or a degradation of the geomaterial. Good examples of these two mechanisms would be MICP, upgradation. When you say microbially induced calcite precipitation, the two particles of the soil might get cohesed because of the calcite which is getting precipitated. So upgradation is occurring. But you will realize that if the geomaterials are consisting of enough fraction of organic matter, then rather than upgradation, the chances are the material might degrade or decompose. So it depends upon how you want to utilize the system. As an environmental geotechnologist, where my principal aim is to decompose the municipal solid waste, degradation of geomaterial is more welcome. But suppose I'm trying to, let us say, reinforce the desert sands. I want to create some temporary structure. This is where I would like to use MICP to put the particles together, form a bridge, and form a unit which is going to be a cohesed unit. So in simple possible form, the basic model would be like this, that you have geomaterials, soils and rocks, and they provide enough parking space for bacteria because of the charges present on it, or the microorganisms which are present on this. Because of the environmental effect, these geomaterials might be parking cations also on them, and then there might be a situation, there is a film formation over there, and this system comes in contact with another particle, another grain. So between these two is the interface, and as a geotechnologist, I'll be very eager to see what are the characteristics of this interface which is getting generated. One of the ways to do this could be if I measure the suction, and this suction is going to be biosuction. So the first question or the first shift which comes from the conventional geomechanics where the suction is measured to biogeointerface would be how to measure the biosuction. And please remember one thing, that biogeointerface is going to be a function of temperature, pressure, salinity of the solution, its pH, and the type of geomaterial which is being used. As I said, what is the relevance of biogeointerface? Why we shifted our focus from conventional geomechanics to environmental geomechanics, and one part of environmental geomechanics deals with the biogeointerface. A good example which comes to my mind is generation of methane gas. Now, this methane gas might be generating in the landfills, okay, and then we try to utilize this landfill gas for energy generation, energy consumption, which is a good example of microbial activity, where the degradation is taking place. And suppose there are favorable conditions and pressure and temperature, this also gets converted into the hydrates, gas hydrates. So my research group is quite prominently working in this area of gas hydrates, where the biogeointerface gives us a good opportunity to learn how microbial activity under conducive pressure temperature conditions under the bioactivity would create gases which might become the source of energy. So these are what is known as methane gas hydrates, and they are supposed to be the future source of energy, and their extraction is becoming a very big challenge. But of course, if you want to do sustainable development, where we talk about the renewable energy or the green energy, methane gas hydrates are supposed to be fulfilling these requirements. Some other good examples of biogeointerface on which we worked in the past are activated fly ash, construction debris, blast furnace slag, and industrial waste, and converting them into zeolites. Well, there was a time when I was working on biogeolites, but then somehow I got distracted. I stopped my work in this area, but this seems to be a very promising area, and I hope that one of you would take it up further and go ahead. So idea was to soak the zeolites with the biomaterials and make them as biofertilizers or bioconcrete. Another good example of these type of zeolites could be controlled drug delivery, where the porous media can be utilized for dosing with the pharmaceuticals or the dose of the drug, which might go in the stomach and may release slowly, and the controlled form of the release of the drug or diffusion of the drug or the pharmaceuticals. Such type of zeolites can also be utilized for environmental cleanup, like bioremediation, particularly oil spills, nuclear waste, sludge and waste water treatment. So there are several applications. It's fortunate or unfortunate that I shifted my focus, as I said, and I'm not anymore working in this area. But I thought of speaking out my mind and trying to enthuse some of you who would like to work in this area to make things more, relevant. So again, the question is, what is soil suction? In simplest possible form, is the volumetric moisture content or gravimetric moisture content. When it is plotted against soil suction, you get SWCC. Provided you have measured the soil suction, and provided if you have SWCC, you can do wonders. You can find out all the properties of the soils or the geomaterials. But the question here is that soils cannot be devoid of microorganisms and bacteria. And the type of mechanisms which I have shown and the type of mechanisms which I have discussed so far, particularly in the form of biogeointerface, they are bound to happen. And when they are bound to happen, how would you measure the suction which is getting introduced because of the bioactivity, and how SWCC would get influenced because of the biosuction? Now, it's understood when biogeointerface develops, the soil fabric will change. Soil mineralogy might also change. Good example is sands. And sands, when coated with the calcite, look what has happened. The mineralogy has changed. The fabric could also change like this because of the alterations in the pore solutions. How will you incorporate them to obtain the shear strength, soil permeability, bacterial flushing, or retention, compressibility, and how the flux would migrate from these type of soils? When I say flux, this could be the flux of the heat, flux of the chemicals, which is chemical concentration. It could be the flux of the current, or it could be magnetic flux also, or it could be combination of everything, or it could be radiations. So everything put together, how they are going to influence the material, and once the material is getting influenced, how its suction response would change. This is a multi-dollar question. It requires some efforts from the researchers and see how this could be taken into account. So shift in the perspective is that so far we have been talking about total suction being made up of metric suction and osmotic suction. And we understand that metric suction is because of the capillary forces, adsorptive forces. However, the osmotic suction is because of the presence of salts. But based on the discussion which I just had with you, you must have realized that soil being a material which provides enough opportunities for bacterial activity, microorganisms to grow and harp on it, you cannot ignore the biosuction term. So how would you measure this is my question. And if Professor Digitol is hearing this, and I know that he's a champion in developing these type of suction measurement devices, I think some effort should be made to create biosuction devices where we can filter out from the total suction the influence of the microorganisms and bacterial activity. So the question is that if biosuction is to be taken into account, what would happen to the fitting functions, SWCCs, which all of you are aware that these are the functions which are used for finding out or establishing the SWCC. And once the SWCC gets established, I can work out the unsaturated hydraulic conductivity, heat migration, and contaminant transport, and so on. But the question is that once another component gets added up to the suction, which we discussed just now in the form of the bioactivity, whether these curves are going to be valid or not. So in this case, we further got shifted towards the multi-phase of the geomaterials. And I should acknowledge the research which is being done by my research group is really very, very absorbing. So my postdoctoral student, Dr. Arif Mohammed, he worked on municipal solid waste decomposition. And this is where we wanted to understand how the pore fluid characteristic changes once the material decomposes. And this decomposition could be at extremely high temperatures. So the type of gases which are going to generate due to decomposition, whether they get diluted into the pore solution or not, leachates. And particularly in case of, let us say, bioreactor landfill, where you are recirculating the leachates to decompose the waste, what could be the mechanism? So imagine if I have sensors which are biosensors, I can install them in the landfills, and I can sit in my office and see on the computer console that how suction is building up. All right. Right now, what is done is that we measure the temperature of the waste, and then we recirculate the leachate to decrease the temperature, or again to enhance the decomposition process. My another PhD student who is about to finish his PhD is a champion in multi-phase geomaterials, gas hydrates, which I was talking about. I'll show you some examples in another couple of minutes that why gas hydrates are becoming a good example of multi-phase geomaterials. My another PhD scholar is Mr. Goli, who's trying to develop composites from the waste, and this waste comes out from the municipal solid waste as well as from the industries. And then we are trying to create different states of the composites by varying their composition and creating a new construction material. My another PhD scholar is working on the waste rubber, and this work is just in the initial stages. This again is going to be a multi-phase geomaterial, example. My another PhD scholar is working on thermal consolidation. What would happen when you would heat materials which are having very high organic matter in them? So the logic and simple understanding says that organic matter is prone to decomposition at high temperatures. And decomposition would create three states of the material, or three phases of the material. One is the solid phase, the residues, another one would be the leachates, and the third one would be the gases. So imagine you are decomposing organic matter, which is going to create three forms, or the three phases of the material. I would like to understand what is the micromechanics of this process. How would you monitor it? Are there some sensors which are available for this? And what's happening at the pore scale? So this can also be studied with the help of suction measurement. But then this suction is going to be totally different than what we discussed just now in the form of metric suction, osmotic suction, and the biosuction. Now, this series of my students, they are very actively working in the energy geotechnics. Mr. Rao, who is dealing with the methane CO2 replacement, where we would have loved to see how a molecule of gas gets replaced by another molecule of the gas, and at that time, how suction of the geomaterial changes. So this is what is known as CH4CO2 replacement. That means once you have created hydrates, and if I want to harness more and more methane, it's a good example of CCUS also, carbon capture, utilization, and storage. So you may say that by doing CH4CO2 replacement, we are also trying to capture CO2 and trying to store it and utilize it. Another student is Fakira, and she is working on geothermal energy from abandoned gas oil wells. It's a beautiful example of how multi-phase gets created at elevated temperatures. So those of you who are working in the field of geothermal energy would realize that the geomaterials are constantly being exposed to very high temperature gradients. And because of that, a multi-phase of the material gets created over there. Can I monitor this? My another student is Kamran, and he is working on carbon capture utilization in industrial byproducts for neutralization, mineralization. This could also be leading to the dissolution of minerals. And of course, Jayashree Navaluri, she is working on carbon capture utilization and storage for enhanced oil recovery. And of course, my undergraduate student, she is working on AI/ML in environmental geomechanics. So these are the people who are forcing me, I would say, to learn the multi-phase geomaterials and geomechanics. So let me explain to you what I mean to say by multi-phase of geomaterials. Unsaturated soils, where we are talking about osmotic suction and metric suction, we could quantify the process with the help of soil water characteristic curve. So in this case, what happens is you have the soil microstructure would be, you have minerals, then you have unfrozen water, and you have gas. And different type of studies have been done, like how fluxes migrate, contaminant, current, heat, and so on. compressibility, shear strength and all. Now suppose if this system gets exposed to extreme pressure and temperature condition, that's what is happening in the nature, plus microbial activity. So this becomes a beautiful example of multi-phase geomaterials. So if I want to conceptualize this multi-phase geomaterials in the simplest possible form, a good example would be frozen soils. Sub-zero temperatures, could be high temperature, could be normal temperatures. Now cryosuction is going to get developed. Why? Because we have mineral states, mineral phase, we have unfrozen water, we have some part of the water which has got frozen, and then we have gas trapped into it. So this becomes a beautiful example of frozen soils. And this is where the call of the day is to use the word SFCC, that is soil freezing characteristic curve. Now, once you know soil freezing characteristic curve, where again you will have to measure the suctions when the material is undergoing phase transformation from liquid to solids, ice, let us say. All right. Or in case of hydrates, there might be a situation where under very high pressure and low temperatures, the methane gas might get trapped in the water and it may crystallize. So what type of phases we are going to create over here? We have the mineral structure. We have free form of the water. We call it as UCW, unclathrate water. We have clathrate water. So clathrate is something, it's a crystal of ice which has been formed from the water and it traps inside gases. In the marine environment, it could be methane, pentane, butane, or the entire series. In municipal solid waste, we could have the basic minerals, the basic organic matter. We could be having leachates, which would be having gases which are getting generated at high temperature. And there might be an interplay between these phases of the material. So when we talk about gas hydrate bearing sediments, we try to develop SCCC, that is soil clathrate characteristic curve. Now I'm sure you must be realizing that when we deal with multi-phase of the geomaterials, which might happen in nature, your slopes are going to get affected. You know, petroleum reservoirs are going to get affected. The storage tanks on the ground, which you are making to store different types of chemicals and liquids, are going to get affected because of the heat migration and so on. So this becomes a very, very complicated matrix. So this is where actually we are, and we are struggling. And we'll be very happy if one of you can give us a way forward, because my idea is to measure what happens when the multi-phase gets generated. Can I observe it? Can I detect it? Can I see how suction is changing over a period of time? How the phases are getting formed, freezing for that matter. Dissociation. Dissociation means the clathrate, which was having methane gas trapped in the water and crystallized and created something similar to the mineral matrix in the soil mass, is now melting. It's releasing the methane gas. How this phase change can be tracked, how it can be measured. So the implications are very interesting and very intricate. Fluid transport, particularly water, methane gas, carbon dioxide. The examples which I gave to you just now, ocean bed subsidence. The more and more gas you withdraw from the ocean bed, the chances are that the entire sediments may get subsided. Well, so we tried to develop some SFCCs by conducting basic experiments. So my understanding is, my student Lijit is working on this and he's submitting his thesis, that if you consider this phase diagram of the geomaterial, and if I look into the microscopic structure, I would be having the mineral surface, and mineral surface is bounding the unfrozen water, and in between I'll be having the frozen water. What is the interplay between these three surfaces is a question. So what unfrozen water is going to do? The unfrozen water would depress the freezing point. Number one. It would generate cryosuction, and cryosuction is going to impart strength to the material, and that's what is going to happen when the material is freezing. The clathrates are getting formed. So nature has given you hydrates in the seabed. The seabed is stable. But when we want to extract energy out of these hydrates, we want to dissociate them by applying energy or depressurization. And that is the time when the strength loss might occur, which would result in complete collapse of the seabed. Subsidence, we may call it. Another good thing which might happen is the cryosuction which is getting generated would decrease with the decrease in temperature. We are talking about minus ranges. So -10 to -20 to -30. Why? Because the water is disappearing. Again, I am reiterating, I want to see how water which is trapped and is unfrozen is getting utilized in formation of the hydrates. That means suction must be decreasing. Is there a method by which I can measure the suction? Would these tensiometers work in the sub-zero temperature ranges? What should be done further? This requires some thinking. How I'm going to check the capillary action, adsorb water and solute concentrations when this type of state of the geomaterial is getting created. So what is SFCC? The SFCC in the simplest form is when you are freezing the soil mass, starting from, let us say, saturated state of the material. So we are moving in this direction. Initially, we had unfrozen water. The moment we cross the zero mark, we enter into the sub-zero state. What happens to unfrozen water content? It starts depleting. What happens to the volumetric ice content? It starts increasing. So this is what actually is, in other words, known as soil freezing characteristic curve. Very much similar to SWCC, what we have discussed earlier. If I know SWCC by measuring suction with respect to moisture content, I can predict all fundamental characteristics of geomaterials. Similarly, under freezing state of the material, if I can develop how the water content from the pores is getting utilized for formation of ice or clathrates with decreasing temperature, this becomes a SFCC. Applications would be several. So once we have done SFCC, it's going to be very, very useful for all your applications related to hydrates, energy extraction from gas hydrates, EOR, enhanced oil recovery, and of course, up to a certain extent to the geothermal also. These are the three current topics on which most of the geomechanics guys are working. So establishment of geomechanical characteristics, which would also deal with fluid conductivity. Why fluid conductivity? Because when I'm extracting gases from the sediments, the water will also come out. Compressibility, how the entire matrix is going to get compressed, and ultimately the net effect would be subsidence of the seabed. Shear strength, loss of shear strength, and of course how the heat is going to migrate from one point to another point under these type of situations are the latest ideas, which researchers are trying to work on. What we did is we did some initial experiments by keeping the water in a freezer and measuring its impedance. And impedance is something which would tell me what is the relative permittivity of the soil mass at different temperatures at different times. So it's just like a camera I'm trying to use, when the phase change occurs, when a saturated soil is going to become a frozen soil, what happens at that instance? How the relative permittivity is going to change. One of the ways to show this could have been if I was able to measure suction. And then I would have compared the results. I would have been very happy. So right now we are doing mixing models by using the permittivity of different phases of the solids, which are minerals, ice, unfrozen water content, the air which is present in the soil mass, and their relative permittivity. And these are all single point measurements. All right. So that means a movie cannot be created out of how the phases are changing. And then you can compute the ice volumetric ice content by using these steps and by knowing the permittivity and the beta value which is normally assumed at this moment. So truly speaking, these models have to be validated. Though all this is a published work, but we are still not very happy and satisfied, and we want to go one step further. Now let's consider for a time being the soil cathode characteristic curve, SCCC. So we have the mineral surface, we have unclathed water, and methane or carbon dioxide gas gets trapped and forms a crystal. Multi-phase system. What's going to happen to the fundamental properties of the material? So when you have unclathed water in the system, water is in the liquid state, capillary action would be there, and when capillary action would be there, the solute concentration is going to be different with respect to temperature, pressure. There could be a decrease or increase in the amount of unclathed water which we are talking about, and hence the fluid flow and the shear strength would get changed. So what are the challenges forward? Challenges are that very, very grossly we are assuming that when we freeze the soil, the 100% of the water gets consumed to form ice or clathrate, which is not correct. I would have loved to measure it at that particular moment. How to measure cryosuction? And then what is the influence of the thin layer water interface? How it is going to influence? And once you know the suction at this point, you can also coin the term effective stresses in multi-phase geomaterials. So this is what the future of geomechanics is, I suppose. So some time back, I showed you a shift in the perspective in suction measurement. Now I'm talking about another shift in the perspective. And the another shift in the perspective is that we have total suction, which would be equal to metric suction plus osmotic suction, plus biosuction, and plus cryosuction. And this cryosuction is an offshoot of extreme pressure and temperature conditions. And let me reiterate, this is the state of the material, which is very, very significant for all those who are working in the field of energy geotechnics. This is the state of the material, which is very significant for the people who are working in the field of degradation, upgradation, disintegration of geomaterials, let's say MSW, municipal solid waste. So these are the questions, and this is how I think we have to go ahead. That means geomaterial is getting exposed to various loadings, different types of stresses, mechanical, chemical, thermal, electrical, radiological, biological. And all these stresses might be acting under cryogenic conditions, low temperatures, high pressures. This has to be included. How geomaterial would respond to these type of stresses and these type of extreme environmental conditions. Once we can master this, this would be the holistic approach towards geomaterial characterization. And that would also be including biogeointerface and cryosuction. And I hope you can realize that both of them are ultimately responsible for doing design and changing the concepts of the geomechanics for sustainable development. This is a place where most of these activities are taking place. This is my laboratory. You are welcome to visit it. I'll be more than happy to receive your comments and suggestions how to proceed further. challenges are tremendous. And I don't think I'll be able to handle all these challenges. So the best way is to speak them out and hope that somebody will come forward and take up these challenges. Thank you very much. I should acknowledge the inputs and all sorts of teaching which my research scholars have done to me. Examiners of various theses who have made us what we are today. Reviewers and editorial board members of the journals. Without their help and comment, we would not have learned even a bit of this subject. And of course, the funding agencies who have been very generous to show, a lot of generosity and give us funds. And thank you very much for being a part of this pursuit. Thanks a lot.
Thank you, sir. Thank you for the wonderful ideas that you have given and you always give. But yes, the challenges ahead of us is huge, I would say. And it is always wonderful listening you and learn so many challenges where we try to understand one behavior and we try to climb up one ladder, then you give so many ladders. So it becomes really, really difficult actually to see that where to start from and where we are going. And so that is what we always try to, so being your student at IIT Bombay, we always try to enjoy your lecture like a movie, and never thought of making that. But yes, we are now on the path of climbing the ladders very, very slowly. We don't know that where it will lead, but yes, there are a lot of challenge in geomechanics where only the saturated soil mechanics cannot handle. And of course, the unsaturated soil mechanics, there are so many components that we have to bring. And as you have highlighted some of them where we have to bring the contaminant, we have to bring the bio-geo interface, we have to bring the radioactivity, we have to bring so many things together in order to understand the geomaterials in a way that it should be understood if you want to master it. So really, it was wonderful to listen. And so thank you very much for the wonderful presentation, I must say. So thank you, sir, for your wonderful time. And
if time is there, I would like to listen Professor Digitol's comments on my hunch and my questions.
Yes, definitely. So I would request the panelists to kindly switch on the camera if it is all right, and to share the perspective. So Professor David, if you are there, and Professor Ashraf, Dr. Aizat, so please.
I would certainly love to respond, Ashutosh. Thank you very much, Professor Singh. That was wonderful. And as Ashutosh has said, you pose more and more challenges for us. I think I'll start by just a very pragmatic answer that that would be interesting to explore. You talk about the cryo aspects and the freezing process, and that is something that we've given a little bit of thought to, but nothing as much as you have. But I think it should be possible to saturate our tensiometers using glycol, which I think has a freezing point of about -12, -13 degrees centigrade, that would at least allow you to continue measuring through that transition point, even if you couldn't go to very low temperatures. We haven't done that, but that's certainly something that would be great to explore. And as you say, just to see the simple thing as to what happens to the suction as it goes through that transition would be really exciting to be able to do that. What the question you raise around the bio area, as you say, you nicely summarize the process of capillarity due to surface tension, adsorption due to intermolecular forces, and then osmotic suctions due to solute concentrations. And my question really is, are those not the same processes that the bioorganisms are actually creating? So although the driver is the bioorganisms, what they're actually doing is producing the same processes that we already recognize as part of matrix and as osmotic suction. And as part of that, we've given quite a lot of thought to how plants actually affect our soils. And clearly, roots of plants actually have semi-permeable membranes, and osmotic suction is what actually drives water across that boundary. But the effect on the soil is to create a matrix suction in the soil, even though it's osmotic processes that are drawing the water out of the soil. So I'm just wondering whether we need to create this new category of biosuction, or whether it's not just bioorganisms creating these things in a different way.
One good example of my hunch would be when microorganisms are there in the soil mass, the pH would change continuously. The concentration of nutrients is going to change over a period of time. And this is what is going to change the complete pore solution characteristics. There could be microbially induced leaching also of the soils. So these are, of course, these are the topics and ideas for the further research. I hope you'll agree with me, but yes, I'm like, this is what we feel is going to be the process. You know, nothing remains constant. Everything becomes a function of time.
Yeah, I guess so. So as you say, all the soil chemistry is changing, and the question is whether that acts differently in terms of the osmotic suction that we've been thinking of, which is in terms of just simple salt concentrations, maybe does need to be revisited. You may well be right in that. It's going to be pushing us beyond our comfort zone in terms of these questions.
Another thing which comes to my mind is when you talk about MICP, microbially induced calcite precipitation, that's a bioactivity, and the mineralogy which was very predominant of a soil mass because of the camouflaging effect of the calcite might get diminished. So even the metric suction is also going to get changed. Similarly, you might be having a situation where the minerals are getting, oozed out or dissoluted because of the pore fluid characteristics, and that is microbial phenomena. So overall, neither the metric suction is going to be constant nor the osmotic suction is going to be constant. I mean, we have to think about some parameters which are going to balance these two.
Well, as you say, it's interesting to think about whether we need to identify new forms of suction, or whether we just recognize that there are different processes that are producing them. That's yeah, very, very interesting. Thank you very much.
Thank you very much.
Ashraf, would you like to put final words? Ashraf, you are muted.
Yes, I would like to thank Professor Singh for the nice talk. Actually, he raised a lot of questions and a lot of challenge. And maybe just a question for him, actually. Okay, things are, as you know, are complicated. If we add another category for measuring suctions, then how, or for classifying suction, then how we can practically measure that, or how we can separate the effect of the different category.
Oh, we were successful a bit in showing the influence of biosuction on metric suction and osmotic suction. We have published this paper also, where we have shown there's a distinct effect because of the microbial activity. And from this point onward, this thought became more concrete that if we do not eliminate the bioeffects, suction is going to change. Well, this is a point of discussion, and well, I can forward you that paper. I can send you that reference. And
very interesting work.
Because most of the guys are working on precipitation, dissolution. in the realm of environmental geomechanics, where the entity of the grains do not remain same. It's a intricate arena.
Thank you. Any final comments? Aras, would you like to add anything?
No, I think it's an interesting topic actually to think of, and I think Prof. Singh introduced a new, some sort of area, but it is all linked to what we know about unsaturated soils. It's just the other way that the contribution of these bioorganisms that basically change some properties of this soils and like generate some sort of suction. So overall, it's, I think, just quite interesting topic to think of, whether it is going to be a new area with a new branch of formula, equations, and framework to think of would be something, or fitting in a framework we already have by introducing some new properties would be another way to do it. But quite interesting. I'm looking forward to look at the papers of Prof soon.
Yes, wonderful. Yes, certainly these are the challenges that are ahead of us. But if you see that if you are designing an infrastructure, and Professor David, Aras, you as well, and Professor Osman, so you would recall the challenges that were present in the Wind Africa project in order to design the pile foundation and understand the behavior of pile when it is subjected to wetting, drying. So that was really difficult to bring in when we were trying to understand things by doing the numerical modeling. So there are so many challenges, and if we keep adding them, then the problems become bigger and bigger. What I have understood with Professor David, he always tried to make things very, very simple, and so that the things can be brought in practice. So we'll see that how, if we will keep adding other challenges that are ahead of us and the challenges which exist in the environment, then how things can be understood to better accuracy. So with this, I would certainly thank all the speakers and for their immense contribution and wonderful lectures which they have given. It was really nice listening, and I'm sure all the participants must have enjoyed, and it was wonderful to listen. So one thing that I would like to request, if those who are able can switch on their camera so that we can take a group picture of the event that we are doing. And so we will make it in the mode that where the group picture can be taken. So can you do it? Yeah.
Can I switch my camera?
So, yes, please. You all panelists, all participants should be able to switch on their camera now. And then we will take the snapshot. So some of you please take. Then screenshots you can take. So multiple screenshots we are trying to take. So that is why we are taking a bit of your time. So
We can see that you have a lot of students all around the table. So I see that it seems that in India, you all forget about COVID and pandemic. We are trying to forget it too. So we should have sort of in-person meetings and these sort of workshops.
We are in a closed campus.
In person soon. So we're looking forward to that.
We have noted your commenters. Thank you. Thank you very much. And tomorrow we will see each other again. And thank you for the wonderful participation. Thank you very much. See you tomorrow. Thank you very much.
Bye.
Thank you.
Thank you. Bye-bye.
Yes, sir.
Thank you all the professor.